Hello everyone, my name is Serdar Kara. I'm a second-year computer science student at Bilkent University. Today I will be demonstrating my Phys-102 project named as Magnetic Force on a Current Carrying Wire. The objective of this experiment is investigate how magnetic force on a wire changes with current and magnet separation. Here is introduction and here's the theory. The theoretical foundation of this experiment comes from electromagnetic principles established by Ampere and Faraday. When a current-carrying conductor is placed in a magnetic field, each moving charge experiences a force perpendicular to both its direction and direction of motion and the magnetic field. And for a wire length with length L, the magnetic force is given by F equals I multiplied by L cross B, where I is the current and B is the magnetic field strength. Additionally, the magnetic field between two magnets follows the inverse square law, like B is inversely proportional to the D square, where D is the separation of magnets. For this experiment, I'm using a DC power supply providing a consistent voltage, a spiral-shaped copper wire as our conductor, two neodymium magnets creating a uniform field, a precise scale with 0.01 grams accuracy, a multimeter, and various resistors to get various I values, current values. Here you can see my setup. This setup does the background works for me. For example, it has a precision scale in there and it has cables in the like green field. Here the procedure comes. First, I will fix the magnets at a precise distance using this non-magnetic spacer. Then I will measure the initial mass of our spiral wire using this precision scale. Next, I will connect our wire to the power supply. Here you can see the power supply through this resistor. But as you can see, the resistor is inside this setup. You can see the button there. When I change this button, the resistor changes and I get a different current value. And by changing resistors, I will vary the current from 0.5 to 5 amperes and observe the force changes. This entire process will be repeated with magnet separations of 1 centimeter and 2.5 centimeters, as you see. After repeating these steps, I get the data and the results. I took photo of some of them. Here you can see I get like 1.51 grams for 5 ampere, and here you can see I used the 2.5 centimeter magnets. These are all the large magnets, like 2.5 centimeter separation of. Here you can see it's like it gives 0.2 grams for 0.5 amperes with 2.5 centimeter separation. Here another one, here another one, another one, and another one. After I repeat these experiments, I collect my data. And as you can see in the graph, our results clearly show a linear relationship between current and magnetic force. As current increased from 0.5 to 5 amperes, the force increased proportionally, confirming F, the force value is proportional to the current value. Here you can see the table for 1 centimeter separation. And here, let me change. Here's the table for 2.5 centimeter separation. As you can see, the values are proportional to the value of I in there also, like linearly proportional. And in this table, I want to show that magnetic force, the strength of magnetic fields is inversely squared with the separation of the magnet squared. As you can see here, the magnetic force measured is 0.04 for 1 centimeter separation and 0.01 for 2.5 centimeter separation. And this values confirms this formulas. Here, I want to get the error percentage for different values of current and separation, and I calculate the force uncertainty and the percentage. Like I get at least 18.1% error for 1 centimeter separation and at most 24.3 percentage for again 1 centimeter separation. And here is the other ones, the 2.5 centimeter separations, least and most percentage errors. And let me change. And here you can see the linearity of the graph. Like the yellow one for is 1 centimeter separation, and the orange one is 2.5 centimeter separation. This again confirms the linear relation between F and I. The I is the current value. And here is again this plot is for the show that B field is inversely proportional to the destination of the magnets. Here you can see this is for the 5 amperes, and the value for magnetic force is like a bit higher than 0.05 for 1 centimeter separation, and it's like 0.16 for 2.5 centimeter separation. And it shows the inversely proportionality with the separation of magnets. Let me change. And here I want to talk about the cause of errors. Our experimental values were consistently gives 12 and 24% errors, like lower than theoretical predictions. This systematic error likely stems from heating effects in the wire affecting its resistance for sure, and like non-uniformity in magnetic field. Here you can see this is the 2.5 centimeter separation magnet, and here the part of it is broken, so it might not be produced uniform magnetic field. And the errors may cause from small measurement uncertainties. And the consistent error pattern across different measurements validates our experimental approach despite these limitations. And here, here's my again conclusion. This experiment successfully confirmed the linear relationship between the current and magnetic force, as well as the inverse square relationship with magnetic separation. These results validate fundamental electromagnetical principles that have applications in everything from electrical motors to particle accelerations. And, and my slide is over. Thank you for watching.